Okay, so let's start today's lecture. And before we start, any questions? So are there any questions from whatever we have covered so far? So if there are no questions, so let's just continue. In the last lecture, we actually saw how the concepts that we had seen for continuous time can be used for systems to find out the output if we know the input x and we know the impulse response h. We had also seen that for discrete time, what convolution means. This convolution operator, if we use it for discrete time, what does that mean? And for continuous time, what does the same operator mean? So for discrete time, this convolution operator means convolution sum. And for continuous time, it means convolution integral. So we are going to continue from the same level and see that how we can use this concept and find out output for any given system if we know the input and if we know the impulse response. So in this slide set 6 that we started last time, we saw that if we are given h of n or we are given y of n, both of them, or if we are given, let's say, difference equation of this shape, both of these things are good enough. We can be given this or this, either or difference equation. Both of them help us in finding out the output for any given input. If we are given h of n, then we find output for any given input using the convolution sum. We know that it is going to be just convolution of x of n with h of n. Similarly, if we are given difference equation, then we can just plug in value of x of n here and then find out what is the output for any given input. And these two things we saw are one and the same thing, because from here we can reach here just by replacing x of n with delta n. That is going to give you the output h of n. So input, if input is delta n, output would be h of n. So we saw that how easily we can get your impulse response from difference equation, provided that we have a FIR. If we have an FIR or feed forward sort of terms in difference equation. Now what it says right here is that it is possible that we can have the same impulse response for multiple systems. But you will notice that for FIR systems, it will have a unique impulse response, but you may have non-linear systems which may have the same impulse response. The good part is that for this course we will not deal with any non-linear system. We will just deal with linear system only. So if we are having a non-linear system, it may also give you the same impulse response as a particular linear system. But this confusion you will not face during your undergrad or major part of your masters. So we are not going to deal with non-linear systems. Okay, now we'll see certain properties of convolution operator. So before we continue further, any questions so far? I will ask again. Anybody having any questions in whatever we have covered so far? Any questions? Okay, so if there are no questions, so let's just continue with first of all the commutative property, and then we are going to see further. So let me just ask, did we finish slide set number 5? Any volunteer? Did we finish completed slide set number 5? Because right now we are continuing with slide set number 6. Did we finish slide set number 5? Can somebody respond? Any volunteer? Did we finish slide set number 5? Am I audible to you guys? So right now I can see 14 attendees. So we did not finish slide set 5?
Yes, sir.
So where were we in slide set 5? So where were we in slide set number 5?
Continuous example, sir.
Okay, example. So it was, I believe, 2 examples were given there. I may have covered 1 example, but let me quickly do that other example and then we will cover this slide set 6. So let me just so this is the example that we had already covered. In this example, we are given x of t, we are given h of t, and we covered that how using these two we can find out the output. Your output y of t is nothing but convolution of x of t with h of t, and this convolution for continuous time is convolution integral x of tau h of t minus tau d tau, and then we just plug in the values of x of t and h of t here, and we see that we end up getting this value right here. And how do we end up getting this? We covered it last time very quickly. I will just do it again. So we are given x of t, which is e raised to power of minus at ut, a very famous signal, very common signal. It is exponentially decaying signal starting from 0 to infinity. And this h of t is given, which is simple step signal u of t. So y of t, we know that it is just convolution integral minus infinity to infinity x of tau h of t minus tau d tau. We just plug in your values and this ends up giving us minus infinity to infinity e raised to the power of minus a tau u tau, and here we end up getting u of t minus tau d tau. So this is what we end up getting. And if you see this integral, we talked about it, we have 2 step signals inside integral, and these step signals have the effect of changing the limits, because these step signals are 0 for a certain range and 1 for the other range. The range where it is 0 will make the whole thing 0. We will not consider that range. Only the range where it is 1, that is going to be point of interest for us. We are just going to consider that. This u of tau will be having value 1 for tau from 0 to infinity. So we know that what is u of tau? It is this. This is your u of tau. It is having value of 1 from 0 all the way to infinity. So if you see this, this is going to have value 0 from minus infinity to 0, and it is going to have value 1 from 0 to infinity. So it will be just this range 0 to infinity that we will consider, where this step signal is 1. Then we take the other step signal u of t minus tau. Now the other step signal, we will see that how does it look like. U of t minus tau is a step signal which is this. U of minus tau will be flipped. U of minus tau plus t will be shifting it right here. This is your u of t minus tau. This is your, sorry, tau axis. This is your tau axis. For tau axis, t is some constant and going all the way to infinity. So this t, if you see here, if we have this t which is a positive value from 0 to any positive value, then u of t minus tau will be this. If t is having any negative value, it will be just behind this. Now in this range from 0 to infinity, our point of interest, if t is positive, then u of t minus tau will be 1 from 0 to t. If t is negative, then throughout this range it will be 0. So we are going to have two values here from 0 to t e raised to the power of minus a tau 1 and 1 d tau. This will be value for t greater than equal to 0, and for t less than 0 it will be equal to 0. So if you see this, we end up getting the same thing that you see on your slide. In your slide set, you just directly see this. You're given this thing, you're given this thing, and directly they show that y of t is from 0 to t e raised to the power of minus a tau d tau for t greater than equal to 0. And for t less than 0, within this range, the whole thing becomes 0. So how do we cater for this t greater than equal to 0? We will see this. So from 0 to t, we just plug in the values. First of all, find the integral. Integral will be e raised to the power of minus a tau, the same thing, divided by the differential of this thing, which will be minus a. And limits are from 0 to t. If we take 1 over a common, inside negative sign, we'll take 0 first, it will be 1 minus e raised to the power of minus at. So you can just check it. This is, I believe, what we are going to get for t greater than equal to 0. And for t less than 0, it is equal to 0. And just to cater for that, we just write yt is equal to 1 over a into 1 minus e raised to the power of minus at ut. This multiplication of ut ensures that t always is positive, greater than equal to 0. So this is that answer that you see right there. So this multiplication of u of t, multiplication by u of t, what implications it has? It actually means that this function has values of t which are going to be positive only. It cannot have any negative value. So this is what we covered last time, and we already saw that how this thing is there and what is the meaning of this u of t. So this is that example that we covered last time. And let's see the second example. Second example, again we are given x of t, we are given h of t, and we have to find y of t. The steps are very similar. It is going to be convolution, which is convolution integral, e raised to the power of 2 tau u of minus tau, which is your x of tau, into h of t minus tau. H of t minus tau will become u of t minus 3 minus tau d tau. This is what we are going to get right here. And then again we have two step signal, this step signal and this step signal. Let me do it separately. So let me just write it here. We are given x of t, which is e raised to the power of 2t u of minus t, and we are given ht, which is u of t minus 3. So y of t, we have seen it is going to be integral minus infinity to infinity x of tau h of t minus tau d tau. We just plug in the values from minus infinity to infinity. It becomes e raised to the power of 2 tau u of minus tau, and this becomes u of t minus 3 minus tau d tau. This actually becomes this. Now two step signals, u of minus tau, u of t minus 3 minus tau. So let's just see those signals. So let's first see u of minus tau on a tau axis. This will be just this signal right here. So this value will be 1 starting from minus infinity all the way to 0. And from 0 onwards it will be 0. So it will be from minus infinity to 0 e raised to the power of 2 tau into 1 into the second signal, which is t minus 3 minus tau d tau. Is that right? Then we see the second signal. The second signal is this, shifted by t minus 3. and this is from minus infinity to this. This is 1. This is your tau axis. This is some constant value t minus 3, and this is your u of t minus 3 minus tau. So u of minus tau, we just add t minus 3 to it. Adding t minus 3 makes it come here. Now if we see in the range minus infinity to 0, if t minus 3 is greater than 0, if t minus 3 is greater than 0, I'll just write it here. If t minus 3 is greater than 0, then this will become integral minus infinity to 0 e raised to power of 2 tau into 1 d tau. This becomes this. And if t minus 3 is less than 0, if t minus 3 is less than 0, then it ends up becoming something like this. It is just going to stop here. This will be your t minus 3. Then your limits are going to become from minus infinity to t minus 3 e raised to power of 2 tau d tau. This is what you're going to get. So we just can find out the value of y of t just by solving the integral. Integral itself will be e raised to power of what? 2 tau divided by 2 from minus infinity to 0 for first case, and we can just plug in the values. And if you plug in 0 here, it will become, you can take 1 by 2 outside, inside will become 1, and if you plug in minus infinity, it becomes 0, so it will be just 1 by 2. And for second case, we'll see that it actually becomes 2 tau over 2 from minus infinity to t minus 3. This will become half. Inside we are going to become e raised to power of 2 t minus 3 and minus 0. So two answers. This is for t minus 3 greater than or equal to 0, and this is for t minus 3 which is less than 0. So two answers you are end up getting y of t. So in both these examples, the steps are kind of common. The complexity lies in finding out what is the effect of these step signals. Specifically, this one at times confuses people that how this whole thing is going to look like. Remember that whenever you have this u step signal, this step signal will have value equal to 0 within a certain range and value 1 within a certain range. And for the range where the value of the step signal is 0, we just discard that because it will make the whole product 0. And value where it is, a range where it is valued at 1, that range is the one which is going to give us our limits. For example, if this u of minus tau, if you see, this is u of minus tau, it is 0 from 0 to infinity. 0 all the way to infinity, it is 0. So we're not going to consider this range. So limits where it is 1 are from minus infinity to 0. So from minus infinity to 0, it is 1. Rest of the range, it is 0. So we end up getting this. Then we consider the second one. This is your second. Now the range where we have to see the step signal is from minus infinity to 0. From minus infinity to 0, this function, this step signal will be 1 if your t minus 3 is greater than 0. So if t minus 3 is greater than 0, this value will become 1. And if t minus 3 is less than 0, then from minus infinity to t minus 3, this range will be 1 and rest will be 0. So we are going to have two steps right here, and then we just solve the integral and write the two answers. One answer end up becoming 1 by 2. The second answer end up becoming 1 by 2 into e raised to power of 2 t minus 3. So we're going to end up having two values like that. Any confusions here? So if you see, the same thing is written right here. So we see that for the range where t minus 3 is greater than equal to 0, your becomes minus infinity to 0 e raised to the power of 2 tau d tau. The answer is 1 by 2. And for the range where t minus 3 is less than 0, this ends up becoming minus infinity to t minus 3, and it is 1 by 2 e raised to the power of 2t minus 3. This is for t minus 3 less than 0, and this is for t minus 3 greater than 0. So two ranges right here, and we end up getting our answer. So if you want to plot it also, you can just see that for how this y of t ends up becoming just something like this. But typically we don't ask for a plot for y of t, but this question I believe was asked last time, that do we have to plot y of t. In this course typically I don't ask for a plot of y of t, and for that matter I typically don't ask for a plot of any function apart from very simple functions like step signal or shifted step signals, these types of signal, maybe exponentially decaying signal, e raised to the power of at ut type of thing. So those simple signals you should know how they look like, but more complicated looking signals typically I don't ask for any plot, because this is basically a signal and system course where the understanding part is important, not a mathematics course where you are expected to know the plot of all different types of functions. So this was the second example. If you compare the first and second example, the steps are quite similar. The complexity arose in how we deal with the step signal and how the step signals are changing the limits. So initially we just write convolution integral, plug in the values and see how many step signals we end up getting, and the step signals are supposed to change the limits. And how do they change the limits? That is where the difference is there between the first and second example. In first example, the step signals were quite straightforward. We could just judge that what is the range of those step signals and how we can change the limits for that. In second one, the step signals, especially this one, was comparatively, you can say, more complex. So you have to see that for what range this value will be 1 and for what range this step signal will have value equal to 0. And accordingly, we have 1 and 2 types of y of t. Okay, so this was the two examples, and this is slide set number 5, and all the summary of whatever we covered. We saw that how we can extend the concept of convolution to continuous time by just using the concept that any continuous time signal can be expressed as integral of scaled shifted impulses. Now integral or summation of scaled shifted impulses mean one and the same thing. The only difference is that integral comes in where we are trying to sum up or trying to take summation of a continuum, and in continuous time we have a continuum, we have a continuous type of a thing which we are trying to sum up. That's why summation ends up becoming integral. So using this concept, we actually came up with the convolution for continuous time. We know that impulse delta t gives impulse response h of t. Any shifted impulse delta, let's say t minus tau, any shifted impulse will give you shifted impulse response. And if we have a scaled factor with this, the same scaled factor will come with your response. And if you have a whole, you can say integral or summation of these, it will have a whole integral or summation of the same thing. So integral of x of tau delta t minus tau will give you integral of x of tau h of t minus tau as a result. So this is your convolution integral. So this concept you will see is very useful and will help you find out output for multiple different continuous time systems. So again, you can use convolution in your Matlab, but this will be covering in your labs. And these questions in Oppenheim and Wilsky are practice questions which you can use for practice. So just slide set number 5 that we actually saw last time, and we completed both examples here. So with this, we'll come back to your slide set number 6. Before we do that, any questions? Any questions with the example that we saw? So if there are no questions, then let's just again continue with your slide. So let's just continue with your slide set number 6. And I'm sorry, whenever I change slides, I have to just go out and come back again. So just maybe a glitch of a second or so. Okay, so let's come back to your slide set number 6 and see what we were covering earlier. In slide set number 6, you will see that we are going to use the same concepts of convolution that we covered in slide set number 4 and 5 for discrete time and continuous time. This is a very interesting slide set, and here you will learn about a very simple technique of simplifying system. Now, what is that technique? We are going to see in a few moments. Let's first just go over the basics. So we saw for discrete time what convolution means, for continuous time what convolution means, and we saw multiple different examples for discrete time and at least 2 examples for continuous time of how to find out output if we are given input and impulse response. And we covered this also, that we can completely describe a system if we are given impulse response or if we are given the difference equation. Typically, a single difference equation will result in a single impulse response. For nonlinear system, we may have a similar impulse response, but we are not going to consider nonlinear system in this course. Okay, so just let's continue with slide set 6. In this slide set, we will see few properties of convolution operator. Starting with the first property. First property is known as the commutative property. In this property, what it says is that the order in which we do convolution does not matter. We can take convolution of x of n with h of n, or we can take convolution of h of n with x of n. It will give us the same result. So convolution of h of n or with x of n actually means h of k x of n minus k. And if we do the reverse, convolution of x of n with h of n actually means this, k equal to minus infinity to infinity, x of k h of n minus k. So both of them are one and the same thing. You do this and you do this, you will get the same result or same answer. So order of convolution doesn't matter. Later on, we will see that at times it helps if we just change the order. It helps us in simplifying the convolution solution. Similarly, for this was for discrete time. It is valid, whatever we are covering the properties, it is valid both for discrete time and continuous time. So order here also doesn't matter. Convolution with h of t of x of t actually means h of tau x of t minus tau, and convolution of x of t with h of t actually means integration minus infinity to infinity x of tau h of t minus tau. So whether you do first integral or the second integral, you will see that you will end up getting the same result. There will be no difference. So this is the commutative property, that order does not matter. So this convolution operator, we call this as an operator, it has this commutative property. An interesting thing to notice is that this convolution operator obeys the same properties as your multiplication operator. So either we can multiply a with b or we can multiply b with a, it will end up giving us the same result. If this is c, this will also be c. So very similar to the property of a multiplication operator. So this operator. Any questions? Okay, so very similar to this multiplication operator. Multiplication operator also obeys this commutative property, that order in which we do multiplication doesn't matter. So in here also, order in which we do convolution doesn't matter. It will give you the same result. Okay, now comes the interesting part, starting with the distributive property. Distributive property is if we are, let's say, having convolution of x of n with sum of two things, h1n and h2n. Then what can we do is we can just open up the brackets and write it this way. It will be convolution of x of n with h1, and to that we can add convolution of x of n with h2n, and we will see that we are going to get the same result. Either we can just add these two together and then do convolution with x of n, or we can do convolution of x of n with h1, convolution of x of n with h2, and then add them together. It is going to give us the same result. This is known as distributive property, and very similar to the property that we saw for multiplication. Also, we know that we have something like this. If you have something like this, we can just do it this way. So this multiplication operator also obeys your distributive property. So very similar to that, your convolution operator obeys this distributive property. Now this distributive property is used in parallel system. If you remember, a parallel system is a system where the input is the same and output, we just add them together and we get the final output. So these two are known as the parallel systems. The output of this system, x of t is input, its impulse response is h1t. So the output here will be, we can just write x of t convolved with h1t. Similarly, output here will be, this input is x of t, the same x of t, and output is y2t, which is x of t convolved with h2t. And if we add them together, it will be this plus this. That will be your y of t, this plus this. So if you see here, it is very similar to this. We can have continuous time or discrete time, and continuous time, the same thing is written right here. So if you want to find out the output, what we can do is we can just add the impulse response of these two systems and make one equivalent system right here. The output of this equivalent system will be, if you see, it will be x of t convolved with this h1t plus h2t. So instead of having two systems in parallel, if you want to have an equivalent of this, equivalent system will have just these impulse responses added together. So this is the implication of this distributive property. We can simplify parallel systems because your convolution operator obeys your distributive property. So if we have parallel systems like that, we can just add together your impulse responses of parallel system and come up with h of t, which will be equal to just h1t plus h2t. Now it is true not only for two systems, we may have more than two systems in parallel. We may have 3, 4, 5 systems in parallel. So the equivalent system would be just adding together all the impulse response of these parallel systems and just having one equivalent system right here. And it is valid for both continuous time and discrete time. So if you have parallel systems, we can simplify parallel systems by having one equivalent system, which is having impulse response that is sum of all the impulse responses added together. So this is the implication of distributive property. It is used in simplifying parallel systems, and we can simplify those parallel systems and come up with a single equivalent system. So this thing we are going to use later on in multiple domains, in multiple areas, in practical real life also. So this distributive property, a very useful property which helps us in simplifying parallel systems and finding out an equivalent single system. Okay, both for continuous time and for discrete time. Any confusions? Anybody not very clear on this? Okay, similarly, let's have another property. I will just skip this example. Let's have another property, which is associative property. Now, associative property is used for simplifying serial systems. How? First of all, what is associative property? If you are having h1n convolved with h2n and the result is then convolved with x of n, then what we can do is we can just change the order and convolve x of n with h1 first, and then the result can be convolved with h2. Because convolution actually takes two inputs, we just convolve two things together. So if there are three things which are being convolved, the order in which we do convolution doesn't really matter. Again, very similar to your multiplication operator, that also obeys the same thing. If we have something like that, what we can do a multiply by b first and then multiply by c. It's one and the same thing. So similarly, your convolution operator also obeys your associative property. This is known as associative property. That order in which we do convolution doesn't matter if you have to convolve multiple things together. Now this associative property actually helps us in simplifying serial systems. Example is right here. Now this is again valid for both discrete time and continuous time. So let's see an example right here. So if we have, let's say, two systems in series or cascaded together like this, and the final output is y of t. If you see here, the output of after the first system would be x of t convolved with h1t. We are calling it wt right here. And this is given as an input right here, and the output that you get right here would be again your wt, which is x of t convolved with h1t, and this whole thing gets convolved with h2t. We end up getting this thing as a result. Now what we can do is we can just simplify this system and have one equivalent system, and that equivalent system impulse response h of t would be h1t convolved with h2t. So as a result, the output y of t would be x of t convolved with h of t, and h of t we know is h1t convolved with h2t. So if you compare this with this, this is your associative property. So we can just take these two convolved first and then convolve with h2, or we can convolve x of t with this. So implication is this: if we have series systems cascaded together, so instead of having two systems, we can just make them into one single equivalent system, and the impulse response of that equivalent system will be this. It will be h1t convolved with h2t. And again, this is true for continuous time and discrete time, and you will see that even the order doesn't matter. We can just take h2 first and take h1 later, and either we can have h1 with h2 or h2 with h1. It will all give you the same result. Order doesn't matter, and also the order in which we do convolution also doesn't matter. So we can simplify this into this, or this into this. And even if we have more than two systems, if we have more than two systems, maybe 3, 4, 5 system, h3, h4, h5 in series, then we can just reduce all those serial systems into one single system, and the impulse response of one single system would be convolution of all the individual impulse responses. So instead of having multiple series systems, we can just have one single system whose impulse response will be given by convolution of their individual impulse responses. So that is known as the associative property. Now, before proceeding any further, let me just give the implication of what we have seen so far. So we have seen that how we can simplify systems into one equivalent system. So let's say if your engineering team has designed a system which comprises of multiple systems. If your engineering team comes up with a design that comprises of multiple different systems, which are, let's say, something like that, and the input is x of t and output is y of t, and these multiple systems have got their individual impulse responses as h1t, h2t, and we can just keep writing this h3t, h4t. So this whole type of thing is known as structure. So the structure of your, let's say, design is something like this. Some signal processing system is designed by your engineering team, and it comprises of multiple subsystems which are having this type of a whole structure. Now, in your, let's say, organization, if let's say two engineers are there, one engineer sees that structure and then works day and night and maybe works for about 3 months, 6 months, and just patches all these systems together, makes a whole, let's say, complex system, and then tests it out and shows it and is very happy with his achievement that okay, he has patched the whole system correctly and came up with the right result. Now the other guy in the same organization, actually instead of spending maybe 6 months working day and night, just works maybe for about a week, maybe less than that, and then comes up with a simple single system H of t, and the very last moment he just walks in with his simple looking thing. Now this whole thing may be a huge circuit with all that complex things patched together and giving us the result, and this may be a very simple looking thing and giving you a particular result. Now this Mr. Engineer may be expecting his promotion after working day and night for 6 months and patching it correctly and finding out the correct result, and this guy may be expecting that this particular person was sleeping most of the time and may get fired for this and just came up with this simple looking thing. But practically what will happen, this guy may get fired and this guy may get a promotion. Instead of just working day and night, he worked intelligently and smartly. So this is the difference between an intelligent engineer and a hard-working engineer. So we expect an engineer to be a smart person who works intelligently. We have to engineer the simplest possible solution, because if we patch up this whole huge thing, this will give you exactly the same result as this one. All we need to do is, if you see here, these two are in series or cascaded together, so we just combine them together. It will give you one impulse response. This will give you one, this will give you one, and so we have 1, 1 and 1. Then parallel systems, we just join them together, again single. So then 1, 2, 3 and 4, again we just simplify and end up getting an equivalent system right here. This one, to be very exact, would be something like this. So this one will be something like this thing, convolved with the summation of H3t convolved with H4t plus H5t convolved with H6t convolved with H7t and plus you have H8t, this whole thing convolved with H9t. So we just do convolution one by one and end up getting our final result, which will be your H of t, and this will be a single system. Now the single system, the beauty of this would be that it will end up saving you a lot of component, lot of silicon space, lot of, let's say, cost, lot of power. All those things can be saved, and we will end up getting a very simplified system which is equivalent to this. So this is the implication of those two properties that we saw, that how can we simplify parallel and serial systems just by using the properties that we saw, the associative property and the distributive property. Distributive property actually helps us in simplifying parallel systems, and your associative property ends up simplifying our serial systems for us. Now this example is again an example where we have to find out output given the input and impulse response. So if the input comprises of two set of signals, we can deal with them separately. So we can just deal with this as, let's say, x1n, this with x2n. So first we just take convolution of these two, and then we take convolution of these two. That way we can just simplify. If we take convolution of, let's say, let's call this as x1n, let's call this as x2n. So convolution of this is a and un type of thing, a and un with un. We have seen this example earlier. It will end up giving you y1n as a result, which will be something like this. And this is again your a n u n type thing, where let's say you have u of minus n. So we have seen an example of this also, and you will see that the result of this will be this, and the final result will be y of n, which will be just sum of y1n and y2n. So we can just deal with those types of signals separately. So yn is just x1n plus x2n convolved with h of n. It is y1n is just this, and y2n is basically the other one. So you can just add these two together and get your results. So this example is actually solving for all that. Now, as far as getting this result, I believe if you go over the previous example, it is very similar to what we have done earlier. So how do we get this and how do we get this? That can be easily seen. Now, if you get a result like this, 2 raised to the power of n for n less than equal to 0 and greater than equal to 1, we can use that u factor with this and write it that way. So for n less than equal to 0, we can just write it as 2 raised to the power of n plus 1 less than equal to 0. This will be u of minus n, and we can just write this as 2. For n greater than equal to 1 would be u of n plus 1. That will make sure that n is always greater than equal to 1. So we can just express this in terms of u also. Just like this u of n, if you don't want to write u of n, we can just write for n greater than equal to 0. It's one and the same thing. So either you write this or write that, that is one and the same thing. Same here. We can either have u of minus n or this. It is just convention. So be comfortable with this usage of step signal to specify the range where the signal is valid. Okay, so we saw different properties, especially this distributive and associative property is a very useful one, because that actually helps us in simplifying complex systems and finding an equivalent system, a simplified equivalent system. Okay, let's just continue. So till now what we saw was certain properties of convolution operator. So let's just talk about some other properties of systems. We saw memory system and memoryless system. We know that memoryless system is a system whose output depends on input value at the same time. Example is an amplifier system. If your output is a scaled value of your input, scaled version of your input, then we have that amplifier system. It's a memoryless system. We don't need to store any previous input or output to compute your present output. So it's a memoryless system. So whether it is a discrete time or a continuous time, to something like this. So output is just scaled factor multiplied with your input. So it's a memoryless system. So if you want to find out the impulse response of these systems, replace x of n with delta n, y of n becomes h of n. So your impulse response actually is this for those systems. In real life, most of the systems we come across are not memoryless systems. They are memory systems whose output depends on not only present input but previous inputs and at times previous outputs also. So we know what these memoryless and memory systems are. We talked about system invertibility, and we said that a system is invertible. Let's say this system is invertible if there exists another system which can undo the effect of this first one. So if output of this one goes here and the output here is same as x of t, then we say that this one is invertible system and this is inverse of this system. This is what we say. Now we have seen two systems cascaded together. So if we just combine these two together, then we will end up getting, let's say, this. So this thing is not right, it is basically convolution. So if you combine these two together, then the equivalent system would be, let's say, h of t convolved with H1t. This will be the equivalent system, single equivalent system. And the effect of this single equivalent system would be that your input will give you an output which is going to be same as your input. So what does that mean? What should this be equal to? And this here says that for the two systems to be let's say inverse of each other, or the second system to be inverse of the first one, all we need is that the convolution of these two should end up giving us an impulse. This is what it's saying. So if H1 is inverse of Hn or H1t is inverse of Hft, then their convolution will give you an impulse. So H of n convolved with H1n should give delta n. So what does that mean? Let me just draw it here. So if we have, let's say, two systems and the second one is inverse of the first system, let's just talk discrete time first. Let's say this one, let's call this H1n, let's call this H2n. Then the equivalent that we will have, let's call that equivalent as H of n. So equivalent is basically convolution of first with the other. Now if this one is inverse of this one, then this convolution will end up giving you delta n. And what does that mean? If this is delta n, then what should be the output? Y of n. Then what should be the output? Y of n. Let's just see that what should be the output. So y of n we know is basically convolution of x of n with h of n. And if h of n is delta n, then it will end up becoming x of n convolved with delta n. And if you do convolution, we will see that what do we get? K equal to minus infinity to infinity x of k h of n minus k. So if we just plug in the values, x of n is same x of n or x of k, and the second one is basically delta n minus k, and this will be same as x of n. Or we can do it in another order. If we just flip the order, if we just change the order of these two, because at times that helps. So that actually means delta k x of n minus k. So both of them will end up giving you x of n. Now why is it so? Here again a very interesting thing. If inside summation you have impulse, inside summation you have impulse. Now this is also an impulse, this is also an impulse. This is an impulse which is this one. On the k-axis it is just this. On k-axis this is just 1. This is your delta k. And this is also an impulse. This is on k-axis a shifted impulse. So it will be on n. So what does that actually mean? This is your delta n minus k. So this k-axis, you flip this, make it minus k-axis, delta minus k of delta k will be still 1, and then delta minus k, you add n to it, it will be shift right by n. So it will be just this, shifted by n. So these impulses, sorry, that's not arrow, it's just 1. Why this summation is equal to same x of n? Whenever inside summation you have an impulse, we can directly write the answer. It will just give you one value, because just like step signal inside any summation or integration just changes the limit, an impulse inside any summation or inside any integration simply gives us a single value. Why? Because this is a product, and this product we have to see sum of this product over the whole range of k, for k equal to 0, 1, 2, 3, and from minus infinity to infinity. But this particular delta k, it has value at only one k, which is at k equal to 0. At all other case, this will be 0. At all other case, this delta k will be 0. This impulse will have value only at one point, and that value will be 1 at that point. And in this case, that point is k equal to 0. At k equal to 0, this value is 1. And at all other points of k, at all other points from minus infinity to infinity, this function, this delta is 0. Only at k equal to 0, this is 1. So at k equal to 0, this is 1, and at k equal to 0, this is x of n. So this whole summation, if you open it up, it will be delta, let's say minus 2 to x of 2 plus n plus 2 and something like that. We can just keep on adding all the terms from infinity to plus infinity. But at all values of k, this delta k is 0. Only at k equal to 0, this is 1. And at k equal to 0, this is x of n. So just x of n. Let's see here. Same delta function. At all values of k, this is 0. Only at k equal to n, this is equal to 1. So if you, this product, if you just open up this summation for this product, this particular term in the product is always 0 and is 1 only at n equal to k. At n equal to k, this is equal to 1. And at n equal to k, the first term is x of n, and this is 1. So this actually shows you that convolution of anything, convolution of with delta n will end up giving you the same thing back to us. It will just end up giving you x of n. So you don't even have to go into the summation part and see anything. If you are convolving anything at all with with delta n, it will always give you the same thing back. And this is true not only for discrete time, it is true for continuous time also. So we saw for discrete time, it ended up giving us the same thing, and same is true for continuous time. First of all, any confusions right here? We just showed you that convolution of anything with delta n, with impulse, unit impulse, ends up giving us the same thing back. And this actually sort of led us to another thing inside summation. If you end up getting this impulse, then it actually simplifies the whole summation, because this whole product will have just one value. You can just see that summation and directly write the answer. And we can take multiple different examples. Let's say we have summation k equal to minus infinity to infinity x of n minus 3 u of n delta n. Sorry, let me just k u of k delta k minus 3. So multiple different terms can be here, but in all that multiple things that you see, if a single impulse lies, it will simplify the whole thing. You can directly write the answer. You know that this whole product is valid only once k is 0. At k equal to 0, this will be 1, this will be 1, and this will be just x of minus 3. So we can just directly write this. So inside summation, whenever we end up getting impulse, it will simplify the whole thing. We can directly write the answer, and later on, once we do examples, it will become more clear. Although in mathematics you should have been told about these impulse and step for integration and summation, but from my experience I know that typically our students are not actually prepared that way, and this is the first time they come across such examples where inside summation or integration they see a step or a impulse function. So be comfortable with this step function and impulse function inside a summation or inside integration. Whenever you see that complex looking summation or integration where you have this step signals and impulse signals multiplied together inside a summation or integration, always just look for this impulse. If impulse is there, you can directly write the answer without going into much detail. And if impulse is not there but step signals are there, step signals always just changes the limit. So we just plug in the appropriate limits and then solve it accordingly. Okay, here we were just dealing with first and second systems, where second system was supposed to be an inverse of the first one. And we said that if second system is inverse of the first one, then their convolution, we just can simplify and make them one equivalent system h of n, and its impulse response would be convolution of these two. And if it is really inverse of each other, then, or they are undoing the effect of each other, then you will see that this convolution will end up giving you an impulse, because then if this is delta n, impulse response is delta n, then output y of n will be same as x of n, because we have just seen that convolution of anything with delta n ends up giving you the same thing back. So this is the key factor right here. And let me do the same thing for continuous time also. So for a continuous time system, let's talk about a continuous time system. Let's have h1t, and then the second system is, let's say, h2t. And if the second system is inverse of the first system, then first of all we can just we know that we can just make an equivalent system which will have impulse response h of t, and h of t would be just convolution of the first with the second. So h of t, we are just simplifying the cascaded system, so the h of t has to be convolution h1t convolved with h2t. And if the second system is inverse of the first one, then this convolution will be delta t, because here also then output would be just input convolved with an equivalent, and this will be x of t convolved with delta t, which will be same as x of t. Now why convolution of x of t with delta t is x of t, we'll see here. So y of t, if you see this convolution part, it is integral minus infinity to infinity x of tau h of t minus tau. And we can take it in any order. We can just shift the order also, just for your, you can say, information. We can do it this way also. So order doesn't really matter. So if you just plug in the values here, it will become minus infinity to infinity x of tau, just we leave it as such, and this is h is delta, so delta t minus tau d tau. And if it was this one, it would be, if you just plug in the limits here and this way, so it will be delta tau x of t minus tau. Now this is an integration, and inside integration we are having impulse. Inside integration we are having an impulse. Now what is an impulse? This is t minus tau, so shifted on tau axis by t. This is tau axis and this is shifted by t. This is your delta t minus tau. And if you see this, this is delta tau on tau axis, it is just this. This is your tau axis and delta tau. Now we know that this impulse has value only at one point only. In the whole integration range of tau, this delta function has value at one point only, and this point for this case is tau equal to t. Tau equal to t, this value is 1 and this value is x of t. At tau equal to t, this whole thing, this becomes tau equal to t, and this is just 1. Same if you see here, this impulse has value only at tau equal to 0. At tau equal to 0, this is 1. At tau equal to 0, this is x of t. So this actually shows us another thing, that inside integration, if you see an impulse, impulse is a function whose value exists at one point only. So if we are integrating this product over a whole range, in this product, this particular term will be 0 in the entire range, and this term will have value equal to 1 only at one point. Only at that point we can just directly write the answer. So inside, if you see a complex looking integration and if you see an impulse in that integration, you can just smile and directly write the answer. So you don't have to go into any deep mathematics. So this is something which is going to be helpful in your solution of future examples. But the take home message otherwise is that convolution of anything with an impulse, convolution of anything with an impulse gives you the same thing back. So if you convolve anything with delta t, you end up getting the same thing back. So this was the take home message from this particular example. So this was system invertibility and looked at in a different way. So if you are having two systems and the second one is inverse of the first one, if we make an equivalent system impulse response is just convolution of these two, and that convolution will end up giving you delta as a result. So if an impulse response of a system is delta t, then you would see that the input will be same as the output, because anything convolved with impulse gives you the same thing back. Okay, so these concepts will be used in control and filtering and so many different areas. Later on we'll see that where all we can see this. And at times if we have to calculate inverse systems, we just use these types of, you can say, equations to compute inverse. So if you have to find inverse of, let's say, h1, and we'll see that what particular thing once convolved with it will give you delta. Same is true here. If you have to find inverse of h of t, we'll see that h of t convolved with what is going to delta t. It is just a check to see whether it is really, this h1 is really an inverse of h of t, or h1n is really an inverse of h of n. So if their two convolution of these two ends up giving us impulse, that means they are inverse of each other. Okay, so next we talk about accumulator systems. We talked about accumulator systems in our introductory lectures. At least twice we refer to this accumulator system. So what is an accumulator system? So an accumulator system is this. This is an accumulator system. This is a system, if we just open this up, you will see that it ends up becoming this x of n plus x of n minus 1 plus x of n minus 2 plus goes on and on and on till infinity. This is an accumulator system. It is accumulating all the inputs till present time. And this is not a very nice way of writing accumulator system. Typically we write it this way. It is basically summation of x of n minus k for k equal to 0 to infinity. Typically we write it like this. So this is an accumulator system. So an accumulator system is sort of it acts as a running sum, or accumulates all the inputs that are there till present time. So if we have to find an inverse system for an accumulator system, you will see that an inverse system would be something like this. First difference, and we can just see h1 as this. Now whether this is an accumulator system or this is an inverse of accumulator system or not, we can check it by just doing convolution and seeing that what the result is going to be. Okay, I'm not very sure whether this is the inverse or not, but it is just talking about what is an accumulator system, and if you want to find out the inverse of a accumulator system, then we can find out inverse using, and we can check whether we have an inverse system by just convolving the two things together and seeing what the answer is. So here the impulse response h of n given as u of n for one system, and this is H1n. So if we just convolve these two together and see what we end up getting, that is going to help tell us whether we are having the same thing or not. So if we just convolve, let's say u of n with this delta n minus delta n minus 1 and see what we end up getting. So this convolution is going to end up giving us u of n, and this convolution is going to end up getting u of n minus 1, and the difference of these two would be delta n. Yes, they are inverse of each other, so it is right. So convolution of this one with this one will do, and if the result of convolution is your delta n, then we will say that we have a inverse system. So in this example, we are actually given an accumulator system whose h of n is u of n, and another system whose impulse response is given to us as delta n minus delta n minus 1, and we have to check whether these two are really inverse of each other. So what we need to do is we need to do convolution of these two. So if we do convolution, we will end up getting u of n convolved with delta n minus delta n minus 1. So we can just open it up and do convolution of delta n minus u of n convolved with delta n minus 1. The first one, we know convolution of anything with delta n ends up giving us the same thing back. The second one, again, it's an extension to the concept of impulse. Convolving anything with a shifted impulse gives shifted version of the same thing. So u of n convolved with delta n shifted one right will end up giving us result which is u of n shifted one right. So it will end up giving you u of n minus 1. We can check it also. So we can just see u of n convolved with delta n minus 1. So if you forget this, you can just check it up. It is basically k equal to minus infinity to infinity, and u of k, and this is basically delta n minus 1 minus k. So we have an impulse right here. So all we need to do is we have to see that where this impulse is. Basically on the k-axis, this is shifted impulse and lying at value n minus 1. This is your k-axis. So this is an impulse. So minus k-axis and k-axis for delta is the same, and then adding anything which is n minus 1 to k is going to shift it by n minus 1. So this will have value 1 only at k equal to n minus 1, and at k equal to n minus 1 this becomes k equal to n minus 1. This is 1, so it is just equal to u of n minus 1, and that's what I wrote right here. So u of n minus u of n minus 1, we know what is u of n. U of n is this. Sorry, this is wrong. U of n is basically this. All ones starting from 0 and going all the way to infinity. This is your u of n on n axis. And what is your u of n minus 1? It is all ones starting from 1. This is 0. So all ones starting from n equal to 1 and going all the way to infinity. This is your u of n minus 1. So if we subtract this with this, the end result is single impulse, which will be just delta n. So we just convolved these two together and found that convolution of these two together ended up giving us this. And the second thing I just explained separately also, that why convolution of u of n with delta n minus 1 ends up giving you u of n minus 1. So as a general rule, convolution of any x of n with any shifted impulse, with an impulse which is shifted, let's say n minus 4, will actually give us x of n minus 4. So this is what a shifted impulse does. So if it is a simple impulse, so if n minus 0, it will be n minus 0. It is n minus k, it will be n minus k. So convolving anything with an impulse gives you a single value. If it is simple delta n, it will give you the same value back. It is shifted impulse to give you the shifted signal. True for continuous time and discrete time. Okay, so where were we? Next comes your causal system. We already know what's a causal system. It's a system whose output depends on. A causal system is a system whose output depends on previous values only, does not depend on any future value. So a causal system only depends on present and past values of input and maybe previous value of output also. It does not depend on any future value. So that's a causal system. So typically real world systems are causal in nature. Now anti-causal or non-causal are theoretical systems. So they are not physical real systems. So at times we are interested in finding inverse of system, but the other point of interest is that that inverse also should be causal. So if inverse systems that we want are not causal, then if it is not causal, then it is, we say, difficult to manufacture. For that matter, if we are talking about physical systems, they cannot be manufactured. So if you just patch up a physical circuit and see that it is giving you a particular output. Now if you want to patch up an inverse system which will just undo the effect of the first system, then we can just take a piece of paper and find an inverse, impulse response of an inverse. Now, impulse response of an inverse that we find, we want that also to be causal. If it is not causal, then it is not possible to patch it up. It's not a practical real system. So that is one point of interest, and we'll go into detail of this thing later on in this course also, but more so in DSP. In DSP, where you will be finding out inverse of systems, making inverse systems, there all these types of things will become very important, that your system has to be causal for it to be a practical system. The other important aspect is that of stability, and that also more so in DSP. Once you come up with a design of your system, the first factor obviously has to be a causal system for it to really result in a practical circuit. But it also has to be stable in case you want it to be made into a circuit, made into a practical system. So you have to have a stable system. Now, how do we actually check if we have a stable system or not? Now, if you remember the very definition of the stable system, we defined a stable system as BIBO, bounded input giving bounded output. That was a stable system. So if you have a bounded input, all your inputs were less than some upper bound physical value B, then we actually can check whether we have a bounded system by just seeing that the output that you get should also be bounded. So if input is bounded by some upper bound, then output also has to be bounded. Then how do we check whether that system has got a bounded output for all practical scenarios. That is done by actually doing convolution, by applying convolution and taking absolute value. So let's just see that what is going on right here. So we are seeing that all your x of n has got an upper bound, some constant b. The output is basically convolution. Some in order of convolution doesn't matter, so we are just taking impulse response first. So it is h of k x of n minus k summed up from minus infinity to infinity. If you take magnitude of this or bounded value of this, it will be magnitude of this thing also. Now then what we can do is we can actually take this bounded value inside, or magnitude value inside. If we take this magnitude value inside, then this equal to sign gets changed to less than equal to sign. Why is that? The reason for that is if we are having value or magnitude of this, then we are just taking the positive part of this, and if we are just taking positive part of both, then the result of the product will be either equal to or greater than your result. So if we have this product, let's say, now this product does not put any limit to positive or negative values of h or x. It can have either positive or negative value. But if we just put a magnitude part here, then it is just positive value. So this product that you get will be either greater than or at the most equal to this product right here. That's why we put a greater than equal to sign here. So the magnitude part inside summation, if we take, we end up getting this greater than equal to sign. We end up getting this. Now the magnitude of all your x's, all your inputs, we know that it's already has an upper bound. Now some of these values may be close to this, some of the values may be very lower than this, but it will never be greater than this upper bound. So instead of this magnitude part, if we put the actual max value right here as b, then we can just be sure that this is the product that we are going to get will always be greater than or equal to your result. So we can just replace it by b, and we have the same greater than equal to sign here, because practically this x can have any value but never exceeding b. So if we put b here, then the product that we get will definitely be greater than or equal to your result. So if we just replace it by a constant b, we can take that constant outside your summation, and we end up getting this product b multiplied by sum of all hk from k equal to minus infinity to infinity. Now in order for this product to be less than infinity, this is already bounded physical value, or you can say a discrete value. Now for this product to be discrete, we want this particular summation also to have a value which is finite. So if this summation is finite, then this multiplied by this will always give you a finite value or a constant value. It won't give you infinity if this summation is not infinity. So if this summation is less than infinity, then this product will be less than infinity. That means your y of n or output will also be less than infinity, or in other words, you will have a bounded output. Let me repeat it again. So what we did was we wanted to see whether our system is bounded input and bounded output. What we did was we put a limit on our input. We are going to ensure that all our inputs are bounded and it is never going to exceed an upper limit b, some constant b. Now this b can be anything. It can be 1, 2, 10, 100, 1000, whatever, but some finite value. It will not infinity. It has some upper bound. So this is b, some value, and all our inputs are less than this upper bound b. So this is our bounded input. Now the output is convolution of input with impulse response, and this is h of k x of n minus k. We take the magnitude of y of n, that means magnitude of this convolution. Now this convolution sum is product of h of k x of n minus k, this product summed up for the whole range of k. Now if we take this magnitude part and put magnitude limit on each term of this product, then instead of equal to sign we end up getting greater than equal to sign, because these two terms may be having a positive and negative part in between. But if we put that magnitude limit here, then we are ensuring that both of them are positive. So this product would be either greater than or equal to this. If all these terms are positive, it will be equal to this. If some are positive, some are negative, then this product that you get here would be greater than your output. So first thing. Next, this magnitude of all x for x and minus k, we know that all our x values are always going to be less than this max value b. So instead of just taking different values here, we can just put a constant value b. All values of x would be definitely less than b, so we can put b here. That is again going to ensure that this product that you get, if we just replace it by b, the product that you get will always be greater than or equal to your output right here. And if this is replaced by b, we can take b outside. So it is b multiplied by this summation. Now why we were doing this, we wanted your output y of n magnitude to be less than infinity. Now in order for this to be less than infinity, we want this product to be less than infinity. Now this is already a constant value, so we want this also to be some finite value. So if this summation is some finite value or less than infinity, then this product will also be less than infinity, and that means your output also will be less than infinity. So it all boils down to this particular condition, that this summation should be less than infinity. And what is this summation? It is basically summation of your impulse response for all values of k. Now the way we actually talk about this term is, we say that your impulse response is absolutely summable. If our impulse response is absolutely summable, then you would see that your output will always be bounded for bounded input. Or in other words, bounded input will give bounded output if your impulse response is absolutely summable. Or in other words, if sum of h of k for all values of k is less than infinity. So this is the condition for stability. And we will see later on that how do we check this particular condition for different systems. How do we actually check whether we have a stable system? By checking out the impulse responses, whether it is absolutely summable or not. So we are going to take up from this particular slide again in the next lecture. So I'm just going to stop here, and before I just stop this lecture, any questions so far? There are so many things we covered in this lecture, starting from properties of you can say convolution operator and how that actually helps us in simplifying systems. Then we talked about inverse systems, and then in the end we also talked about this stability of system. Any questions so far?